Hi everyone, glad to meet you virtually and thank you for coming. This is Lingling, a fourth-year PhD candidate from UT Dallas. Today, I will present my joint work with Professor Metin and Professor Suresh. It's about the optimal subsidies and or taxes to promote electric vehicles under the impact of charging inconvenience. The main motivation to start this paper is observing the fast development of electric vehicles in the last decade. It is well known that transportation sector attributes to the largest portions of carbon emission and oil dependence. So EV acts as an important way to pursue transportation sustainability. In addition, the energy efficiency of EV is 3 to 4 times that of gasoline vehicle. Also, EV enables the development of automobile industry and other related industries such as battery industry. Despite all these promising advantages, EV adoption is still below expectation. It is reported that the global market share is around 2%. So there are still many obstacles. Among them, high purchase price and range anxiety are the most important ones. On average, EV price is 40% higher, and range anxiety mainly comes from two parts. The first is no range, which is about 150 miles for most EV models at present. The other is inconvenient charging, both about non-charging time and no charging network. To promote EV adoption, governments around the world provide several subsidy programs. Most of these programs include incentives for consumers to reduce the purchase price, which is the consumer subsidy in our context, and incentives for charging suppliers to build more stations, in turn to reduce the range anxiety, which is referred as station subsidy. Many previous literature study consumer subsidy program. However, none of them integrate station subsidy. To the best of our knowledge, we are the first to study both programs theoretically. So the main research questions are, first, what is the optimal subsidy structure to subsidize consumers only, charging stations only, or both? Second, what is the optimal number of charging stations to build under the government subsidies? As the government perspectives are different, whether they are equivalent in the sense of yielding the same solution. Also, we want to investigate how do the optimal subsidies change with different conditions. To answer these questions, we model the interaction between the government and the charger as a Stackelberg game, where the government is the leader. So the order of events are, first, the government decides whether to provide a station subsidy S or consumer subsidy R, and the amount for each subsidy. Then the charger decides the number of stations to build, and which determines the charging inconvenience HN for the consumers. At the end of the season, the consumers decide to purchase EVs or not. Each EV sold on market contributes charging revenue rule to the charger. Now let's talk more about charging inconvenience HN. So it is an additional cost assessed by potential buyers when they purchase an EV. We prove that the charging inconvenience is decreasing convex in the number of stations. This result is also validated by our numeric study. So it is based on the real data in Beijing. We consider the travel distance to the stations as charging inconvenience and show it is decreasing convex. To specify, we use linear and quadratic charging inconveniences to solve the problem. Considering this charging inconvenience, the effective price is the actual price paid by consumers after subtracting the consumer subsidy R and adding the charging inconvenience HN. In our problem, we use linear demand model. Now, let's introduce chargers and government's problems. For the charger, he wants to maximize his profit by deciding the number of stations N. The first part is the charging revenue from electric vehicles, and this is the construction cost for the stations built by the charger. The government usually considers two problem settings. The first is budget-driven problem, which is to minimize the subsidy expenditure while achieving a predetermined adoption target A. Here, the expenditure includes the total consumer subsidy and total station subsidy. The other is adoption-driven problem, which is to maximize the adoption subject to a given budget B. We observe that both the objective and constraint functions increase in the consumer subsidy R and station subsidy S, so the constraints are bending at the optimal. We are also curious whether these two problems are equivalent, as they only change the locations of objective and constraint functions. To show this, we write a generic unified model using fx and gx to represent their expenditure and adoption functions. Here, x is a vector. With the result from this generic unified model, we prove the two government problems are equivalent. This is useful in practice because the government can choose whichever is easier to solve and search the solution for the difficult one. Till now, we restrict the subsidies to be non-negative. For a more complete way-in, we also consider subsidy tax problems with no restrictions on the sign of consumer subsidy. So in the following, we will first consider subsidy tax budget-driven problem, and then solve subsidy-only budget-driven problem, and finally obtain the solution of adoption-driven problem by equivalence. Now let's go to linear charging inconvenience. This is the linear formula. Here, beta is the maximum charging inconvenience, and alpha is the rate of drop. In this case, the charger's profit is linear in the number of stations. So the charger builds the maximum number of stations if the coefficient is positive. Otherwise, the charger stays out of the market. Knowing the charger's base response, the government make hard decision, and we can solve the subsidy tax budget-driven problem. The optimal solution is given for no construction cost case and high construction cost case. In the next part, the charger builds the maximum number of stations even without station subsidy. So the government only provides consumer subsidy. In the high construction cost case, however, the optimal solution depends on this threshold LC. Below this threshold, the charger builds 0 stations, so the government only provides consumer subsidy. Above this threshold, the government provides both subsidies, and the charger builds the maximum number of stations. In this subsidy tax context, we find that above this red line segment, the consumer subsidy is positive. Below is negative. And the most interesting part is this triangle arrow, where the government taxes the consumer but subsidizes the charger. So the government can design no expenditure program where the total taxes from the consumer equal the total subsidies to the charger. This no expenditure program is appealing to the government because it is self-financing and easy to implement. Also, we find that if the adoption is above a beta, this no expenditure program is Pareto improving, and this is usually the case. Now we consider budget-driven problem by restricting the subsidies to be non-negative. We find that the optimal solution is the same as that in subsidy tax problem when the adoption is above A0 or the construction cost is more than alpha A0 plus alpha B rho. When the adoption is below A0 and the construction cost is less than alpha B rho, the consumer is negative in the subsidy tax problem and becomes 0 here because it is enough to obtain the adoption below A0. In the remaining arrow, the government only provides consumer subsidy when below this threshold and only station subsidy if above. We also observe that this threshold LC is higher than that in subsidy tax problem because the government cannot use tax to partially subsidize the charger, so the willingness to provide a station subsidy is less. Now, if we fix the adoption level and consider increases the construction cost, we find the number of stations increases. The station subsidy increases first and then decreases to 0. If we fix the construction cost and consider increasing the adoption level, the station subsidy increases and in turn the number of stations increases. For the consumer subsidy, however, it doesn't always increases. It changes from positive to 0 when passing through the threshold. This is because the discontinuity of subsidies in linear case. We also obtain the solution of adoption-driven problem by equivalence. However, for the time limit, we will not discuss details here. Now we move to quadratic charging inconvenience. We will only present the result for strongly quadratic case, that is nominal greater than or equal to this value. You can refer to the paper for the weakly quadratic case. It is clear here when nominal equals 0, the quadratic case reduces to linear case. And this is the charger's best response. Then we can solve the subsidy tax problem, and the optimal solution is given for no construction cost case and high construction cost case. We find that the solution in quadratic case converges to that in linear case if the construction cost is extremely low or extremely high. And the structure difference lies in this no construction cost case, where the solution in quadratic case is more complex. Also, we observe that this threshold LC always increases in linear case. However, in quadratic case, it decreases in no construction cost case. That means the government's willingness to provide a station subsidy increases. This is because the charging inconvenience is more responsive for a small number of stations in quadratic case. Then we obtain the solution for budget-driven problem by restricting the subsidies to be non-negative. Here, the rules of thresholds LQC and GQC are the same as those in linear case. If we fix the adoption level or fix the construction cost, we will observe several similar trends as in linear case. The different one is that if we fix the adoption level and consider increasing the construction cost, the consumer subsidy always increases. In this part, we conduct the numeric study with the location data in Beijing and show that the numeric results are consistent with our theoretic results. By the theoretic analysis in weakly quadratic case, the optimal solution is given by no construction cost case, medium construction cost case, and high construction cost case. So we compute the construction cost thresholds and then obtain the optimal expenditure, optimal consumer subsidy, and optimal station subsidy for 3 construction cost cases. In all the 3 cases, the optimal expenditure increases in the adoption level. That is the monotone increasing property as in our theoretic analysis. Also, as the construction cost increases, the expenditure increases for the same adoption level. We then compute several numeric results for different conditions. The top is for different subsidy types. Here, blue is for pure station subsidy, orange for pure consumer subsidy, and green is for combined subsidies. We find the expenditure of pure consumer subsidy is the highest, and the differences increases as the adoption level increases. The pure station subsidy is as effective as the combined subsidies if the adoption is below 200,000. Beyond this, the pure station subsidy is infeasible. The middle is for longer driving range. When the driving range is longer, the charging frequency decreases, and in turn, the charging inconvenience decreases. So the government spends less in longer driving range case. The bottom is considering the cost of charging time. In this case, charging inconvenience increases, so the expenditure is higher. To conclude, we developed analytical models to study the optimal subsidies under the impact of charging inconvenience and prove the equivalence for a generic model with multiple variables. Applied to our context, the two government problems are equivalent. Then we obtain the optimal subsidies and identify several structural properties. After that, we compute the numeric results and show the consistency with the analytical results. That's all. Thank you.